Our next speaker is Dr. Yuan Li, who is, as I mentioned, a new professor at University of North Texas. And Yuan, are you there? She's going to talk about observational signatures of turbulence in the halo.
Yes, I'm here. Okay.
Excellent.
Yes,
Thanks for joining us, Yuan. I'm pretty excited about this. Turbulence is always exciting, especially after the conversation yesterday.
Yes. Okay, so thank you for giving me this opportunity. I had never thought that I would give a talk with such a title. I'm a theorist, so I'm talking about observational measures. I also mostly work on clusters. So what do I know about halo turbulence? Please allow me to explain. I think that the CGM, the ISM, and the ICM are really tightly related. I think we all agree that the ISM and the CGM are connected, and we have a Slack channel on that. There's lots of interesting discussions there. And I would also argue that the ICM is basically the CGM of the biggest galaxies in the universe. And also, these biggest galaxies are extremely extended. You probably have heard of the ICL, the intercluster light, which is the extended stellar envelope of these brightest cluster galaxies. So technically, the ICM is also ISM. Now, even if you don't agree with my argument, I think we can all agree that all these three M's are multiphase and turbulent. So many of the analysis methods can be shared. Because the ISM study is relatively mature and many brilliant people, including many people that are here, have done a lot of excellent work. A lot of really good analysis tools have already been developed there. And today I'll be talking about one specific tool that I borrowed from the ISM community. Is the velocity structure function. So a velocity structure function is a way to study turbulence. And it's, like I said, widely used in the ISM community. Many thanks to Pengo for a very wonderful presentation yesterday that basically covered all the basics of turbulence. I will just very briefly reiterate the characteristics of a turbulent flow. In a turbulent flow, we see eddies or whirls, swirls, twirls, whatever we call them, of different sizes. And we think there is an energy cascade where big whirls have little whirls, which feed on their velocity, and little whirls have lesser whirls, and so on to viscosity. In 1941, Kolmogorov came up with the famous Kolmogorov power spectrum for a steady state incompressible turbulence. Many of you have seen it, many of you know it. At some large scale L or some small k, kinetic energy is injected into the system and it cascades down to smaller scales all the way down to the dissipation scale. And between the injection scale and the dissipation scale, E is related to K with a power law with a slope of minus 5/3. One can derive this with very simple dimensional analysis. Let's assume that epsilon is the rate of energy injection. In a steady state, this should be equal to the cascade rate, and is also the rate of energy dissipation. So what's the expression for epsilon? Well, since it's energy rate, it should go as v squared divided by some time t. What is t? Let's just use eddy turnover time, which is about L divided by v. And that gives us epsilon is proportional to v cubed divided by L, and there should be a factor there. Lab experiments tell us that this factor is of order unity. So that gives us the relation between velocity and size. So v is proportional to L to the 1/3. And from there, one can easily derive the relation between EK and K. So you have E proportional to K to the minus 5/3. And this is the power spectrum. And this velocity size relation is basically the velocity structure function. So now we have our tool. Before I show you how I use it, let me first review how turbulence was previously measured for the hot ICM. Now I put a question mark there next to turbulence because whenever we talk about turbulence, there's always the debate about whether or not we're seeing turbulence or bulk flow. Here, for now, I'm calling everything turbulence. Any random motion is turbulence here. So on the left-hand side, you're seeing a residual Chandra X-ray image of the central region of a nearby galaxy cluster, Perseus. You can see that there are lots of fluctuations. For example, you see these bubbles that are inflated by the AGN jets. And Irina Zhuravova and collaborators developed a method called it's a modified delta variance method to try to extract information about turbulence from these images. And the delta variance method, interestingly, was also originally developed to study ISM turbulence. So what Irina does is she derives the density power spectrum from the surface brightness fluctuations here. And then she translates the density power spectrum to a velocity spectrum, assuming that delta V over V is proportional to delta rho over rho. And then she could get basically the kinetic power spectrum. And what she found is for two nearby galaxy clusters, Perseus and Virgo, the inferred level of turbulence would give you enough dissipation to balance radiative cooling. That's pretty neat, but it's in disagreement with numerical simulations of cluster AGN feedback, including my own. So in general, we find that shock waves, sound waves, adiabatic processes, and mixing are all more important than turbulent dissipation in numerical simulations. So was Irina wrong? Not really. Now there is another way to measure turbulence in the hot ICM. And it's, I think in spirit, very similar to the absorption line studies in the CGM that we've heard a lot about. So you can look at the lines coming from the hot gas. And this was done by Hitomi. Hitomi was an X-ray telescope with very high spectral resolution. It made one observation before it tragically died. That one observation was staring at the central region of the Perseus cluster. And from these X-ray emission lines, you can measure a broadening. And you say, okay, there's some thermal broadening and non-thermal broadening. So if you say the non-thermal broadening comes from turbulence, you can infer a line of sight velocity dispersion of about 100-something kilometers per second, which is consistent with the Irina's analysis. So does that mean theories are wrong? The sad truth that I found out is that when theories are wrong, nobody really cares except the theorists themselves. So I had to save myself and my fellow theorists. I wanted to bring honor back to the theorists. And the only way to do that is to prove that the previous observations were biased or limited. Now, luckily for me, the centers of galaxy clusters are often multiphase. And we can observe the cool filaments using ground-based optical telescopes with AFUs like MUSE and CFHT, etc. And we can even see some of the cooler components with ALMA. And all of these instruments have wonderful spatial and spectral resolutions. So what you're looking at here is the line of sight velocity map of the H-alpha filaments in the central region of Perseus overplotted on the X-ray image. And usually when people see a map like this, they'll say, oh, look, the motions of the filaments appear kind of random. Now, are we seeing turbulence there? Well, there's one way to find out. So on the right-hand side, I'm showing you the velocity structure function that I've computed of the Perseus filaments. So to obtain this first order velocity structure function, I simply loop through the map, and for every pair of pixels, I record their separation and their velocity difference. Then I just find the relation between pair separation and the mean velocity difference at the separation. And that's shown on the right-hand side. As you can see, on small scales, there is a beautiful parallel indicating a cascade of big worlds turning into little worlds. So we're seeing turbulence. More interestingly, the structure function also reviews the scale where the energy is being injected. That's where it turns around. And that scale is about 10 kiloparsec. That's exactly the size of these X-ray bubbles on the left-hand side, highlighted with the radial contour. So we're not only seeing turbulence, we're seeing turbulence driven by the feedback from the supermassive black hole. Now, in case you're not convinced, I've also divided the filaments into inner filaments and outer filaments by simply drawing that circle. The filaments, the inner filaments in Perseus follow a structure function shown in red, and you see that bump at 10 kiloparsec. The outer filaments in Perseus follow a structure function shown in green, and they don't seem to care about the inner bubbles, which makes a lot of sense. Instead, the outer filaments reveal a driving scale at about 20 to 30 kiloparsec, which is exactly the size of this outer bubble. So it's likely that the outer filaments in Perseus are following turbulence driven by a previous AGN outburst. And then we also looked at another nearby galaxy cluster, Abell 2597, and we saw the exact same story. The inner filaments follow turbulence driven by the inner bubbles, and the outer filaments follow turbulence driven by the outer bubbles. And we've also got ALMA data on this cluster. And we've looked at turbulence traced by the molecular gas that's shown in brown, and it overlaps perfectly with turbulence traced by the ionized gas. So everything is moving together. And lastly, we also looked at the central galaxy of the Virgo cluster, M87. We only have data on the very central region, unfortunately, but still we can look at the structure function of the central filaments in Virgo, and we see again this very beautiful parallel on small scales. And then the driving scale here is about 1.5 kiloparsec, which is exactly the size of the bubbles here, and the size of that cute little jet there that's currently inflating these bubbles. How cool is that? So in all three clusters I've looked at, I see turbulence, and I see that the turbulence is driven by the activities of the supermassive black holes. And now we can also think about what this means for the coupling between the cold-hot phases, which many people here care about. What do I mean by that? I'm asking, do cold blobs move around like apples falling off a tree, or they move around like the leaves which fly with the wind? I've looked at my own pure hydrodynamic simulations. Unfortunately, the structure function of my cold gas is too flat. And I think it's because my cold clouds are too ballistic. And Chao and Wang had a paper out recently where they looked at structure functions of AGN feedback simulations with magnetic fields. And it seems that with magnetic fields, the cold and hot phases are much better coupled, and the structure function agrees really well with the observation. So now that we can use the cold gas as a tracer of the hot gas, we can talk about turbulent dissipation. So first, let's look at how our measurements compare with the X-ray measurements. So the two horizontal lines represent the Hitomi results for the inner and outer regions of Perseus, which more or less correspond to the inner and outer filaments. As I said earlier, Hitomi has excellent spectral resolution, but it doesn't have good spatial resolution, so the results have to be represented with just horizontal lines. Nonetheless, at the driving scale, they agree really well with our optical measurements. The purple line is the Chandra X-ray fluctuation analysis that Irina Zhravlova did for a region that matches the outer region in the optical analysis. And again, it agrees really well with the turbulence traced by the ionized gas shown in green. So there's excellent agreement near the driving scale. However, the dissipation rate on small scales was previously estimated assuming that turbulence would cascade following a Commonwealth relation. What we see here is that the structure function is steeper than the classical Commonwealth turbulence. So the actual amount of kinetic energy that gets cascaded down to smaller scales is much smaller than the previous estimation. So there's actually less turbulence dissipation than you would assume from what you see on larger scales. So that means the previous observations were limited, and I saved the theorists. But why do we see a steeper slope? I don't know. I don't think anybody knows at this point. We had a bunch of hand-wavy possibilities in the paper. My current favorite theory is that black holes are just terrible drivers of turbulence because everything changes on very short time scales. For example, we can estimate the ages of different generations of the bubbles, and they're separated by only 10 to 20 million years. But the eddy turnover time on large scales is on the order of 200 million years. So we just can't ever establish a classic Kolmogorov turbulence from the driving scale. But Mark Voigt has a different new idea, and I encourage all of you to look at his new videos about gravity waves. And now that we can use cold gas as a tracer of the hot gas, we can have some plasma fun. So earlier I said turbulence cascades all the way down to dissipation scale. Where is this dissipation scale? If dissipation is due to speed or viscosity, we would expect dissipation to happen above the mean free path at the so-called Kolmogorov scale. And the expectation is shown as this dashed line. And what you see here is we see turbulence below where you don't expect turbulence if it's dissipated with isotropic viscosity, which means isotropic viscosity is suppressed. And even though particles are no longer directly interacting with each other on small scales, they're still effectively interacting with each other. So the plasma is still effectively collisional, and it's probably because of particle magnetic fields interaction. And the previous constraints, the best constraints from previous studies come from Irina Zhravlova's surface brightness fluctuations. I just want to point out that that was obtained with 12-day-long Chandra observations of Komar cluster. And as someone with a poor person's mindset, I'm very happy to see that our analysis is much cheaper, and we can push down to even smaller scales to constrain the viscosity even better. Now that I've been converted to an observer, I want to look at more systems. I want more data. So a student of mine is currently analyzing more cluster data compiled by Valeria all the various. And hopefully I'll have some update for you soon. And lastly, I just want to briefly mention some of the other correlation functions that people have used in CGM studies. For a while, I thought that I was the first person who did velocity structure function analysis in CGM observations. But Fakri Zahidi pointed out to me that, oh no, I was wrong. About 2 decades ago, people had already done it. So in Rauch et al., they looked at the velocity structure function in the CGM using absorption lines. Now I do know that Cassie Lucas used velocity structure function to analyze turbulence in the CGM simulations done by Drummond Fielding. In fact, my first version of the script was based on Cassie's script. And Jess' work has looked at density correlations of ions in the Milky Way. And very, very recently, in Xu et al., Zhijie Xu, who's a graduate student at University of Michigan working with Joe Bragman, has looked at both the density correlations and velocity correlations for absorption lines in the Milky Way. And I'm very much looking forward to the discussions next week. I hope that they will talk about these interesting results. So to summarize, the CGM of the biggest galaxies, aka the ICM, is turbulent, and different phases appear while coupled. And the turbulence is mainly driven by the supermassive black hole feedback, at least in the central region of the galaxy clusters. And then turbulent dissipation seems to be a subdominant heating source. Isotropic viscosity is suppressed. And lastly, I want to point out that correlation functions are a lot of fun and they're easy to do. So they sit in the perfect position of that Peng diagram that he showed us yesterday. Fun and easy. And they're also very useful. And I also want to say that it's very important for us to learn from each other. That's why I'm so in love with this workshop. I'm learning so much. And we can really learn a lot from the ISM community. Thank you very much.
Thank you very much, Yuan. That was a great tutorial and really broke down some of the things certainly that I haven't understood in the past. So hopefully other audience members got something out of it too, because I think it was really excellent. There are a number of questions. I encourage people to raise their hands. We'll take questions for a little bit and then move everything to the breakout room in the next like 10, 15 minutes. I'm going to take moderator's privilege and ask my question first because I'm pretty excited about this. So the stuff you were showing with the ICM and the infall, and you looked at the function of the drop off in where the motions were. What do you expect? Do you expect a similar power law for or scaling for infall of galaxies into a halo and then the stripping of gas behind those galaxies? So, you know, you have your main halo, you have a bunch of infalling satellites that go in, they get ram pressure stripped or tidally stripped their debris. So you'd also expect some sort of power law to define the behavior of the gas. Does it? I mean, I don't know what that would give, but presumably that's different than the Kolmogorov turbulent scaling.
I think you're thinking about turbulence on top of bulk motion.
Yeah, so I guess it'd like be a cutoff at small scales because the scale size of the individual streams that are coming off that. I don't know. It just seems.
I wish I could tell you, but I have no idea how to remove bulk motion. Okay. I'm working on it. I've been thinking about it. For the cases I was looking at, I was lucky that I could argue there's not a whole lot of bulk motion, right? You can see it from just the velocity maps. But there might be a little bit of rotation there. I think I just sort of waved my hands and said, you know, whatever bulk motion there is, it should cascade. It just goes into the driver turbulence.
It's just a
But I
drive.
agree there could be bulk motion. That's just bulk motion.
Okay.
Yeah, if anybody has good ideas on how to remove bulk motion, let me know.
All right. The first person who had his hand up was Frank Vandenbosch. Would you like to ask your question?
Hi, Yuan. Excellent talk. Thanks.
Hi.
Just being an internal critic, skeptic, let's put it that way. I was wondering, the results that you showed with this power law scaling relation based on the velocity measurements. Of course, there's two issues that I would worry about, and one is projection effects. We're seeing this in projection, and for example, if for some reason the turbulence would be largely confined planar, then depending on the inclination angle, I will see a different slope in my inferred Kolmogorov spectrum. So what is the issue there? And secondly is seeing. You have a finite resolution element, and that will always, of course, at small scale, will drive your delta V down, and that so which can extend to several full width half max, several kpcs. So how are you sure that you're not just measuring a seeing function?
Excellent questions. Those are the two questions that give me lots and lots of headaches. And I'll just say, okay, for the first one, the projection effect. Here, I totally agree with you. We're looking at everything in the projected plane of the sky, but all of these structures are presumably 3D structures. And you can work out sort of analytically, and I think Xiaoxu recently did some work where she showed the analytics of how the projected structure function should be related to the 3D structure function. If we assume that this thing is reasonably thin, then the projected structure function should be the same as the 3D structure function. If it's not thin, then the projected one would be flatter than the real one. And in this case, because we're already seeing steeper than Kolmogorov slopes in projection, the real slopes can only be even steeper. So it won't change the conclusion. It might change the exact slope. But I don't think that in any time soon we can actually remove this projection effect, just because we can't figure out the 3D structure of these things. Now, the second point is another excellent point about seeing. And it's so funny that it comes from you as a theorist. But at first I was like, you know what? I don't think seeing was doing anything, because seeing would affect smaller scales, and I didn't see any change of slope at small scales. But actually our referee asked about seeing again, and I said, fine. So I did an experiment where basically I asked the observer co-authors to run the data through like another seeing simulation to just blur it up again and compare the structure function of the further blurred up map and the one, the original one. And actually seeing surprises the overall amplitude by a little bit, just a teeny little bit, without changing the slope. So that was a little bit unexpected, and I realized, oh, okay, so the seeing doesn't work like a set function. It's like a Gaussian thing, so everything gets smoothed out a little bit. Now, if you ask me, how does this compare with the original pure data photons without any seeing effect? I don't know, because I don't have a space telescope that can give me that. It'd be great if there's a tool to generate the real spectrum, the real IFU observation out of a simulated cluster, then we can really try to better understand the seeing effect. That's a very good question. Thank you.
Excellent. So our next question is from Christoph Fromer.
Yeah, thanks. Excellent talk and great work. I really love this work that you did, Yuan. Now, regarding, of course, interpretation, that's the sort of really exciting part. And I think there the jury is still out, but I think recently Jaron Wang has written a very nice paper, a grad student of Mateusz Ruskowski, that offered actually an explanation of this steeper slope. And his explanation was that the cold phase velocity structure function is driven by is due to turbulent motions primarily driven due to the gravitational acceleration of ballistic clouds. And this, interestingly, happens to exactly give you the observed slope. Now, in this picture, sort of, then the AGN would sort of excite or sort of trigger the precipitation. So that's why you get this scale. And then once you sort of have the cold cloud set up, that would ballistically move then in cluster potential, drive turbulence. And of course, the big question is, how much in this picture do you couple the hot to the cold phase? So what is your view on this sort of somewhat different picture than you proposed?
Yeah, I thought it was the opposite. So I thought that my cold blobs were too ballistic, and the gravitational acceleration would work against having a steeper slope. So my thought is that, and I'm so sorry for being so slow on writing out that paper, but my thought is that when you have gravitational acceleration on these cold blobs, making them going ballistic, you're going to have basically blobs passing each other at very high velocities without knowing about the existence of each other. So then when you run the structure function, you would have very large velocity difference at small separations. And that's just because they're not connected with any eddies. So I actually thought sort of the opposite. Yeah, I mean, it's, I don't think anybody knows, or at this point, nobody has really convinced anybody else. Yeah, and you should look at Mark Voigt's new idea. That's also really interesting. And warnings, he's very convincing.
Okay. We'll take one more question, I think, and then move to the breakout room with this discussion. Marcus.
Hey, Yuan. So you said that the hot and cold phases are very coupled. So what's the evidence for this? I didn't quite get this. And then you refer to MHD simulations that go and show this. What are the parameters within which that actually works?
Good question. It's all indirect evidence, right? The direct evidence would come from hopefully far future X-ray observations where they actually measure the spectrum of the hot gas. Right now, it's all indirect. I mean, at the driving scale or right below the driving scale where IRENA can probe, there's excellent agreement between the two phases. And then at smaller scales, my argument is that in the case of poor coupling, like my own pure hydro simulations, I see a flatter slope than Commonwealth, or than the observed slope. And in better coupled simulations like Chaoran's MHD simulations, you see a more steep slope. And so it's indirect. I can't show directly that they're well coupled all the way down to dissipation scale. No.
Sure, fair enough. Cool.
I think we have time for one more question, particularly since Mateusz is about to give his tutorial and he's next in line. I'll let him ask the question since he won't be able to join the discussion afterwards. Mateusz?
I yield my time to Prasad, Deborah Prasad. I will just comment on this in a moment anyway. So.
Perfect. Okay. Deborah?
Hi, Yuan. Excellent talk, and that is an excellent work. This is less of a question, more like a verification of what I see in my simulations, and I see the steepening of slope in my cluster simulations. But the steepening of slope depends like where it steepens, depends on like at what stage the agent outburst is. Like if the agent is full blown, the steepening is like more like at 10 to 15 kpc scale, while like the stage where the agents have gone out and it's more like a cooling phase now, then the steepening is much more closer. So I do see a steepening of slope, but the scale at which the steepening happens from Kolmogorov, it changes with the stage of the agent feedback.
Interesting. I would say that that agrees with my bad driver theory.
Okay, so we will take a 5-minute rest. Yuan and anyone who is interested in continuing to discuss turbulence and turbulent signatures in the halo are welcome to join the appropriate breakout room where discussion will continue. And yeah, we'll have a short rest, and then in 5 minutes, Mateusz will get started with his tutorial on AGN non-thermal processes.